Okay, so welcome everyone. My name is Nikhil Narayan and I'm an AI researcher slash intern at Cellstrat. So welcome to the Unsupervised Learning series. Today we are going to cover a topic called clustering. So today is just a introduction to clustering session where we will be covering these topics where we'll see what is clustering, the distance functions and two main popular algorithms under clustering, the K-means and K-means plus plus. We also have a couple of code demos where we'll make use of K-means to see how it works and what can we infer from our data. Then we'll also look at few evaluation metrics for unsupervised learning, especially for this clustering, like inertia, silhouette score, completeness score, and contingency metrics. So before we move ahead, I would like to recap what we did in module 1. So in module 1, we covered what are the different types of machine learning algorithms, what are the differences between them. Then we also looked at different types of unsupervised learning algorithms like clustering, association, dimensionality reduction, neural networks, etc. Then finally, we ended that session with advantages, limitation, and applications of unsupervised learning. Okay, so since today's class is on clustering, if I have to define clustering, I would say clustering can be defined as a task of grouping a set of objects so that objects belong to one group, or let's say the objects belonging to one group are more similar to those in other groups. For example, if I have objects in two groups, okay, let's say in this case I've grouped objects based on shapes. So the objects belonging to this group, say group 1, is more similar to group 1 compared to the objects in group 2. That is what clustering is all about, to put it in very, very simple terms. So you can see various applications of clustering, especially in market segmentation, where you can study the behavior of different customers. So in the previous module, I'd given an example of telecom industry where they study the customer data to see what kind of special offers can be given to those special kind of customers. Then it is also used in social network analysis, medical imaging, like to classify different kinds of tumors, etc. Also, it is used in astronomical data analysis. So there are a lot of data in astronomical field where you don't have any specific labels, so you just want to visualize how these data look like. So in all these cases, we make use of clustering. So when you're doing clustering, it's assumed that, let's say we have a data set X where you have various data samples like say X1, X2 up to Xn. Then what you are assuming is that this particular sample can be partitioned into different configurations, right? So let's say I have a data set with multiple data points. Then what you are assuming is that there is a probability of this going to a cluster K. So here we are assuming what is known as a prior probability, which we discussed in the previous session. Okay, so this is a fundamental assumptions in clustering. So if you have a data, then it must be possible to configure them into n number of clusters or regions. So clustering algorithms can be classified into two types. One is called as the hard clustering, the other one is called as the soft clustering. So from the diagram, it's pretty much clear what hard clustering and soft clustering means. So when we say hard clustering, we say that the data point belong to only one cluster. Okay. And when we say soft clustering, there is a chance that a data point can belong to two or more clusters. So one example of hard clustering is K-means, which we'll be discussing today. And example of soft clustering is fuzzy clustering or Gaussian clustering, which we'll be discussing in future courses. So it's not necessary that all the time it could be a hard clustering. Okay, sometimes there is a chance of soft clustering as well, where you might find few data points belonging to two or more uh, clusters. So here in soft clustering, what is happening is that you give a probability or weights to each of the points. So let's say the probability, let's say there are three clusters, okay, 1, 2, and 3. You take this point and you say the probability that it belongs to one is 0.9. Let's say in this case it's 1 because it's not going to belong to any other cluster. So in this scenario, let's say there's a chance that this point belonging to cluster 3 is 0.7, and the point belonging probability of that belonging to cluster 1 is 0.3. So where is soft clustering used? So in the previous case, I was talking about market segmentation, right? So it's not necessary that it needs to be clustered like this. For example, this member can belong to both these groups, right? So in these cases, we cannot go with hard cluster. We'll have to go with soft cluster and see the probability of this data point. What is the probability of this data point belonging to this particular cluster? Okay. So since today we are mainly focusing on hard clustering, you have to remember that in hard clustering, it has to satisfy two properties, that is maximum cohesion and maximum separation. So what does cohesion means? So cohesion means that if you have a data points within a cluster, it should be maximum close to each other. And separation is nothing but the difference between or the distance between two different clusters. So data points belonging to one cluster should be close enough to each other, and data points belonging to two different clusters should be far away from each other, to put it in simple terms. So if you see this nk by n, if it is greater than or very big, larger than 1, then those are your clusters. Okay, that is following maximum cohesion. So what is nk? Nk is nothing but samples belonging to cluster k, and n is the total number of samples. So if you have the samples belonging to a cluster out of the total number of cluster is very total number of data points is very large, then you know that that region is can be considered as one group or one cluster. Those are called as high density regions. So each cluster can be considered as a high density region where you have lot of data points closely packed with each other. Then you have separation region. So what is separation region? So here you have n out by n less than 1. So n out is nothing but number of samples that are outside this circle of radius r. So if you have any points outside this circle, that should be, if that is less than 1, then you know that there is, let's say there's no data points and there's a clear separation. But if you had a cluster like this, then definitely it would violate this property of maximum separation, and then you can not use hard clustering. You have to go with soft clustering. I hope that is clear. So another point what I want to discuss today is about convex and non-convex clusters. You see, algorithms like K-means cannot manage non-convex clusters. Okay, so what is this non-convex cluster? For example, if you have a data set like this, okay, a banana shaped data set, this is an example of non-convex data points. So in convex data point, you assume that uh, for every pair of points, let's say x1 and x2, when you draw a line segment, and whatever points are coming on this line segment should belong to the same cluster. But in this case, it is a non-convex cluster, because if I take 2 points x1 and x2, then I start making points on this line, then you will know that these points are not part of this cluster. Okay, in these cases, when you have these kind of data, K-means algorithm will fail or will not give the desired results. So we should make sure that when we are using K-means, the data should be, or the cluster should be convex in nature. For example, yeah, you can think of this as some sort of manifolds, right, where you have rolled data, like a Swiss roll data. In those kind of cases, you cannot make use of k-means. You'll have to look at some other algorithms. Is that clear? I hope it's clear. If it's not clear, please feel free to ask questions so we can clarify that and move further. For now, I don't see any questions, so
Yeah,
I
no, this
assume
is
that,
good information. It is somewhat new information in our ML course of clustering. We don't cover some of these points, so these are important new information we have learned. So
yeah,
audience, feel free to ask any questions, please.
yeah. So okay, let's move forward. So in clustering, we will be making use of distance function. So what is a distance function? To put it in simple, or like say in an intuitive manner, distance function is a measure of difference between two objects. So in the previous case, we saw I drew shapes, right? And I told these are similar. The objects belonging to this cluster are similar to each other. How do you determine that? For that, you need to have a function that will tell how close or how far they are with respect to each other. For example, if I have a function tell me this distance and distance between these two, if the distance is greater, then I know they are far away from each other and they are not identical to each other. And if they are close, it is the vice versa, and they are similar in nature. So there are a lot of popular machine learning algorithms that use distance function as a core, like k nearest neighbors, the learning vector quantization, the self-organizing map, and k-means clustering. All these algorithms make use of distance functions for clustering. Okay, so there are few commonly used distance measures or functions like Hamming distance, the Minkowski distance, Manhattan distance, and the very famous Euclidean distance. So we will look at these one by one in due course. Okay, the first one is the Hamming distance. So what is Hamming distance? Hamming distance calculates the distance between two binary vectors. Okay, remember, you are calculating the distance between two binary vectors. So you have a vector, two vectors, and you assume that those are binary, like ones and zeros. Now, if you want to take an example, a binary, anything can be written in terms of binary, right? Even these words can be written as a function, as a binary vector. So if I want to know the difference between two words, I can convert them into binary vectors, and I can use a Hamming distance to see whether they are the same or not. Remember, this is very different from a cosine function where you're checking similarity. So this is not similarity, okay? Like you're not checking similarity here, you're just checking whether the words, how many letters in that particular word match with each other. That's all you're checking. So it's very different from cosine function. So please don't get confused with cosine function. And if you are on the right path for now. So
No, so you are saying there is a clear difference between distance metrics and similarity metrics.
Yes,
Is that
yes,
right?
there is.
So they are two
Yes, there.
different things. So there is no overlap whatsoever. Huh? Distance matrix doesn't mean similarity metric.
Yeah, no. In this case, when I say Hamming distance, and yeah, if I take two words, convert them into binary vector, then when you're
Hmm.
finding the difference, you cannot really say whether the words are similar or not, right? Distance and displacement. It doesn't say they are similar. It will just match and see whether how many letters in that two words are matching. You understand?
Got it.
You're
See,
not.
sometimes even in cosine case, we use the word cosine distance, but
Yeah.
that probably means something else, huh?
Uh, there is cosine distance, but we make use of cosine distance to find similarity.
Hmm.
So
Hmm.
you understanding, so that is a different
Yeah.
context. It's popularized in a different context, then that is the reason why I don't want people
Okay.
to get confused. So
Hmm.
I will leave that for now. So
Sure.
Hamming distance, so how Hamming distance works is that you take two binary vectors a and b, and you perform a XOR operation on it. So what is a XOR operation? So let's say I have a and b, okay, the ones and zeros, and I have a XOR of A XOR B. Sorry for the writing. Let's say I have 0, 0, 0, 1, 1, 0, and 1, 1. So A XOR B of 0, 0 will be 0, 0, 1 will be 1, 1, 0 will be 1, and 1, 1 will be 0. So if only one of the parameter is true, the output is true, otherwise it's false. So here, what you do is for Hamming distance, you take two vectors A and B, like in this case, perform a XOR operation, okay, and you get this, and you calculate the number of ones in that. So in this case, there are two ones, and you say the Hamming distance is 2. But what does this mean? So let's see here. So the position 1 here and the position 1 here is matching, and then where else is it matching? So I think somewhere here it should match. So like this, it is trying to see how close the vector. I mean, that would be a overgeneralized way to tell that, but I hope you can understand what I'm trying to say. Is trying to see what all are the similarities within these two vectors. So you just perform a XOR operation and calculate the number of ones in that. So in this case, you have two ones, so the Hamming distance of these two vectors will be equal to 2. Okay, moving to the next function. Next distance function is, okay, there is a point here. It says whenever there is a bit flip, it's counted as 1. Yeah, okay. The next function is the Minkowski distance. So Minkowski distance, I think you would have encountered this word Minkowskis if you have used supervised learning somewhere. So it is nothing but a generalized form of Euclidean and Manhattan distance. So let's keep Minkowski aside. Let's see Euclidean distance. So here, Euclidean distance, if you see, is nothing but if you take a right angle triangle, it's nothing but you are applying a Pythagoras theorem and trying to find the shortest distance between these 2 points. So this is nothing but square root of y2 minus y1 the whole square plus x2 minus x1 the whole square, right? So here, when the p value becomes equal to 2, you get Euclidean distance. So if you replace this p with 2, this is what you get, the Euclidean distance. And when you replace p with equal to 1, you will get something called as the Manhattan distance, which is nothing but the absolute difference between the points across all the dimension. So as you can see here, you are individually subtracting p1 minus q1 and p2 minus q2 to get the absolute difference. So in K-means, or today whatever we are going to discuss, we are going to mainly make use of the Euclidean distance, okay, where we'll be using p-value equal to 2. Now there can be a question, why not use higher p-values like say 3, 4, 5, 6? So what would happen if we use higher p-values? Actually, there have been a study which has been done, and what they have found out is for higher dimension, you know, and for higher dimensions, say in this case it is 2 dimensions, but if you have more than, let's say, 3 dimension, 4 dimension, or like say n dimensions, and when you plot the Minkowski distance on the y-axis and a number of dimension on the x-axis for different p-values, what they found out was, let's say p equal to 2. So this is p equal to 1, you have p equal to 2. After more than p equal to 2, what happens is that this tends to saturate, and you really cannot find the difference between the you don't really find the variation in different p values. So that's the reason why people restrict themselves to use only p equal to 2, which would give us the Euclidean distance. I hope this point is clear. So what I was trying to explain is that since Minkowski is a generalized form of Euclidean in Manhattan, there can be a question, right? Like, why not use p-value greater than 2? So when you use p-value greater than 2 for, let's say, higher dimensional data, it need not be just in 2 dimension. Let's say you have lot of features, right? It's not necessary that you have only 2 features. You will have n number of features. So in those scenario, when you use a higher p-value, it doesn't make any difference, or it doesn't give any difference. So that's the reason why people restrict themselves to p is equal to 2, and you get the Euclidean distance. And today we'll be using Euclidean distance to for k-means. Okay. So since we have completed distance functions and we are moving into the K-mean algorithm, I would like to see if there are any questions. Okay, there are no questions till now, so I'll move forward. Okay, so K-means algorithm. So K-means is one of the most popular unsupervised clustering algorithm. Okay, so it is a vector quantization method that aims to partition n observation into k clusters, right? Like any clustering algorithm, it will take a data set and it will try to split it into k clusters, or different clusters. So what is vector quantization? So see, the k-means was inspired by a technique called vector quantization, which was used in signal processing, where they used to use this vector quantization for data compression. Okay, so there also they used something called probability density function. Since k-means is also dependent on the prior probability, you can see that this vector quantization and k-means algorithm are closely related to each other. Another interesting fact about k-means algorithm is that they are used for image compression. If you want to take a high resolution image and try to compress it without losing too much information, you can classify them into clusters and reproduce them with lower resolution, sort of a compression, data compression. So here, what K-means algorithm is trying to do is it's going to take a data set X, okay, of certain shape M into N. So the objective would be to split that into K clusters, right? K is any arbitrary number which we want the algorithm to classify in. For example, I want a data set X to be classified into 3 clusters, then the value K becomes equal to 3. So what it does is it will take that X, try to split it into 3 clusters like this. So each cluster will have a centroid, and this centroid is nothing but mean of all the data points within that respective cluster. So if I have cluster 1, 2, and cluster 3, each cluster will have a centroid. The identity of this cluster is based on its centroid. Okay, so those centroids are nothing but is represented, for example, let's say for cluster k of j, you will have a centroid mu naught, mu1, mu k. Okay, k for k clusters, you will have k number of centroids. So this top is denoted as for different iterations. So here, as you can see from this diagram, these black dots are nothing but your centroids. Okay, now look at, just observe how these centroids are changing over different iterations. So they are sort of converging to its actual mean, and as it is converging, you can also see the different data points are getting classified into different clusters. So initially you had few number of blue data points. As the centroid of this blue cluster became more and more away from this, T denotes that the centroid, you just don't have one centroid. The centroid varies over iteration. So it should, so then when do you stop this? At some point you'll have to stop this, right? So you try to stop this by minimizing this function s of t. So this is nothing but your distance of the data point, distance between the data point and centroid within a cluster. For example, here this black point and the distance between this black point and all these red data points are calculated for various iteration. And when this value becomes minimum, you stop this. You stop the iteration. Now this cannot be confused to a or this cannot be used as an absolute measure like mean squared error. Okay, this is not a cost function. You will compare whether the distance has changed with respect to previous iteration. So let's say in 12th iteration I have certain distance, and in 13th iteration I have certain distance. So in 12th iteration I have, say, distance d12, and in the 13th iteration I have distance d13. So if the distance is not varying between the iteration d12 and d13, this distance is nothing but distance between the data point and the centroid of its cluster, then we say it has reached convergence and it can stop further classification, further clustering. Okay, so this is what K-means algorithm does. So let me explain how the actual working takes place in 5 simple steps. So if you understand this 5 simple steps, you will know what K-means algorithm is all about. So if I have to put K-means algorithm into 5 steps, this would be it. If you understand these 5 steps, I think you will be very clear how a K-mean algorithm works. Okay, let me explain this. First, you have some random data point, okay, which is as shown in figure A. Then what you do is first you assign a random centroid for this, for k clusters. So here I'm trying to classify it into 2 clusters. So I'll put k is equal to 2. So what the algorithm will do is first it will assign random centroids. Okay, so this is one centroid and this is the other centroid for 2 clusters. Then it will try to calculate the distance between each data point and the centroid values. So it will try to calculate distance between this, for this data point, and between this centroid and this centroid. So like that, it will try to do for each and every data point, it will try to find the distances between each of the assigned centroids. So wherever the distance is minimum, you know, wherever the distance is minimum, it will go into that cluster. For example, you can see that this data point is closer to this centroid compared to this centroid. Hence, it belongs to this cluster. Similarly, this data point is closer to this centroid, hence it will belong to the blue cluster. Okay, and in the fourth point, so you cannot stop here, right? You cannot stop here because this is not the final iteration, or this is not the final step. Okay, now next step what it will do is it will try to find the mean value of the cluster. So now it has initialized into some clusters. Then what it will do is it will try to find a mean value for all the data points for a respective cluster. So for the red cluster, the mean value is somewhere here, and for the blue cluster, the mean value is somewhere here. So once the new mean value is found out, it will again update the centroid. So what is happening is the centroid is changing from this point to this point. So as the centroid changes, again you will have to go to step 2 and calculate the distance. And when you again calculate the distance, you will notice that which was maximum and which was minimum would have changed. Okay, so here you can see that you can see few values getting changed. So here, since it was closer, these data points you can see has become blue cluster, and these data points have become red clusters. So it is changed over iteration. So you will continue doing this until the convergence is reached. So I explained how convergence is reached, right? If there is no difference in distance or difference in mean value, difference in distance between the data points and the mean value for previous iteration or the next iteration, then you say the convergence is reached and you stop this clustering. I hope it is clear. If not, yeah, there is a very good question asked here, or a couple of good questions which is asked here. How do you decide the value of k, and will the cluster vary based on what is the first centroid chosen, or does it always guarantee the same result after convergence? That's a very good question. Okay, so any questions on the algorithm itself, because it's a very simple steps. So if you have any, I'll answer the questions. Before I answer the question, do you have any doubt in the algorithm? Please ask me. Let me see. I don't see any questions. So okay, so let me just summarize this part. So step 1, assign random centroids, then calculate the distance between the centroid and each data point. Whichever is closer, you assign to that cluster, data point to that cluster. Then you calculate the mean value. So once the mean value is determined, your centroid gets updated to that mean value. Again, go back, calculate the distance between the data points and centroid values. Then you continue doing this until the convergence is achieved. Okay. So coming back to the question, is it dependent on the initialization? Definitely yes. This is one of the biggest disadvantages of K-means. It is very sensitive to the initialization of the cluster centroids. So as you can see in this diagram, since
No,
it was
there was a more basic question before. How do you
mhm.
decide the value of k? How
Yeah,
many
I'm
clusters
coming.
you need? Okay,
Yeah,
okay,
yeah,
fine.
I'm coming to that. That
Okay,
we'll
okay,
take that up in the evaluation metrics to see
okay, okay,
whether the k values what we have selected is good enough or not. So that we'll take
okay.
it up in evaluation metrics. But before going to that, I mean, there was a very good question which was asked: is it sensitive to the initialization? Definitely, it is very much sensitive to the initialization. You see here, since the initialization was something like this, it got classified, all this got classified into one big cluster, which is very poor clustering, whereas the ideal clustering should have been something like this. Well, definitely you can achieve this ideal clustering, but the problem is you'll have to run it for n number of iterations. Okay, so if you run it for n number of iterations, yes, over a period you will get this ideal clustering, even when if the initialization is not good enough. But you see, that is not a very efficient technique, right? You don't want your algorithm to run for a very long time to get the ideal clustering, because you want something quick and you want something efficient. So then what do we do? So to answer this or to overcome this problem, people invented something called as K-means plus plus. So K-means plus plus is nothing but a smarter initialization technique and a higher quality clustering. So K-means, the only difference between K-means and K-means plus plus is that K-means plus plus does better initialization compared to K-means. So the rest of the steps remains the same for K-means plus plus. So only at this part K-means plus plus becomes smarter compared to K-means algorithm. So we will just see how K-means plus plus, instead of doing random initialization, how smartly it initializes compared to K-means. Okay, I will come to that point. See, it's actually a very simple technique, but also a very effective technique. How K-means plus plus, initialize the centroid. So remember, these four steps are part of step one in K-means. Okay, the step one of K-means is divided into four steps, and from step two onwards, it is the same. K-means plus plus behaves the same as K-means. So only for step one, it is going. I have put that as in four steps for better understanding. So these four steps all are part of initialization. Okay, please don't get confused. All these four steps are part of initialization of step one, which you saw in K-means. So here, what does it do? First, so if you have selected, let's say, K clusters, it does not randomly assign centroids for all the K clusters. First, what it will do is, it will assign for randomly select first centroid, okay, somewhere here. Only one random initialization. Next, what it does is, it will calculate the distance from the distance of each data point from this initially assigned centroid. So whichever is farthest away, it will select that as the next centroid. Okay. Similarly, it does this for k times. So if you have given it as four clusters, then it will do this 4 times till it finds out 4 centroids, which are much better than random initialization. Another important thing to notice is that when it is selecting the new centroid, it will calculate the distance between the farthest distance between the previously selected centroid. So this centroid was selected based on the distance between this centroid and this centroid, this new data point. So it's not based on this distance. I hope it is clear. So in this way, you can see that initially, instead of just randomly initializing the centroids, it has some meaningful steps it takes to do better initialization. So you cannot say this is a perfect initialization, but it's much better compared
Actually,
to.
step three, I didn't understand. Step three.
Mhm. Okay, so this simply means that if you the next centroid is selected such that probability is directly dependent on the distance to its nearest clusteroid or nearest centroid. For example, uh, the probability of selecting this as the next centroid depends on the distance between this previously selected centroid and the new data point, or the farthest data point from this centroid.
Okay, you're trying to find centroids which are very far from the previous iteration centroids,
Yes,
correct?
exactly. So yeah, so intuitively, if you put it in an intuitive manner, what you're trying to do is you're ensuring that the next cluster is far away from the previous cluster, right? You don't want two
Okay,
points to be closest to each other. So intuitively, if you think,
right.
it's very intuitive that you want the next centroid to be as far away from the previous centroid as possible, so you can
Mhm.
cluster them better compared to, you know. some random initialized clusters where you can have 2 points close to each other, and it will just select. In this case, what we saw, these are too close to each other, whereas you could have just clustered them as one. But if it was for k-means, it would have definitely not put this here, or it would have put that somewhere here or here. So you ensure better initialization this way. Is that clear
Okay.
till
Yeah.
k-means? Audience, any questions? Okay, so if you don't have any questions, I have a question for you. So I was explaining this concept of why non-convex shape fails for k-means. So now you know k-means use Euclidean distance, right? So with this in mind, can you tell me why it fails for non-manifold data points, or like something like a banana shaped data points? Why would it fail? I would let's see. Any answers? Why it will fail? Okay. In the meantime, there's a question asked. It ensures second centroid is farthest from first centroid, but what about other centroids? They might be lying in the second cluster itself. I didn't understand this point. If it ensures second centroid is farthest from the first centroid, but what about other centroids? They might be lying in the second cluster itself if the second cluster itself is farther than all other. I didn't understand this point, but maybe I'll come back to it at the end of the session. So yeah, I got a good answer. It says Euclidean space measure distance between only through straight line, right? It doesn't take uh, the spatial. I mean, if you have in 2 dimensions, it will just try to measure the distance, but it doesn't say those are two. Just based on the distance metric, it's going to say if they are close by each other but on different planes, then it will still classify them as one cluster, but those are totally in two complete different planes, and they had to be classified as two separate clusters. But since the distance was small enough, it it classified them as one cluster, which is not true. So that, yeah, that is the right answer, that since Euclidean distance just measure it as one straight line, does not take the plane into consideration. Yes, that is the right answer. So that is the reason why when you're using a distance metric like Euclidean, you cannot work with non-convex clusters, and it will definitely fail, or it does not give the intended results. Okay, let's go to a code demo of k-means. Fine. So here I'm just going to show you how like implementation of k-means from scratch. It's a very simple implementation. So here, hope it is visible. Okay, let me just zoom in a little. Yeah. So here I'm just importing the required libraries. Okay, I'm just defining a Euclidean distance. So we'll be using this function to calculate the distance between 2 points. So that's what is described here. And then I have defined something called k-means class. So in this k-means class, I'm initializing certain values. So I'm taking certain values as inputs from the uh, user, like uh, how many number of clusters do you want, what are the maximum iterations, and few plotting steps, like do you want to plot or not. Then we are defining the predict function. This is where actually everything takes place. Okay, so inside this predict, you have a lot of functions which I have put in, and I can break this down based on the 5 steps which we have defined. Okay, so step 1 is randomly selecting the first centroid from data points. So here what I'm trying to do is I'm trying to get a ID of the data point, and using that ID I'm selecting a centroid from one of the data points itself. So one of the data point itself is made as a centroid for k clusters. Okay, then in the next step we are calculating the distance between each data points and the centroid values, and assigning the data point to the cluster where the distance between data point and corresponding centroid is minimum. So here what I'm trying to do is I'm trying to first measure the distance between the data point and the centroids of the cluster, and trying to see which is the minimum, which cluster is giving the minimum distance, and I'm taking that index and I'm inputting this data point to that particular cluster using the help of index, and then we will get the required cluster. Next, what we are going to do is calculating the mean value. So once the initials the centroid has been assigned, next would be to calculate the mean value of the cluster and assigning the mean value as a centroid. So here I'm for the given cluster ID and clusters in the particular given cluster, I'm trying to take the mean of all the data points within that cluster, and then assigning the new centroid as that cluster mean. So we will continue doing this for n number of iterations, or when the solution is converged, until the solution is converged. So when does the solution get converged is when the distance between the old centroid and the current centroid becomes equal to 0. We can say when there is no difference between the mean of the previous step and the mean of the next step. That is when we say it is converged. Okay, so it has different functions assigned for each step. Now let's go back to the class and see how it is done in a flow. So I'll try to share this collab notebook. If you can, like, you can try it out for yourself later. So here I'm trying to get all these values. Okay, I'm trying to define a list for the clusters. So number of clusters will be equal to k values. So I assign k number of lists. Then I take, for predict function, I take the data point. Okay, and I try to see how many samples are there and how many features are there for that data point. Then here, as I explained, randomly select one of the or n k number of data points as a centroid. Then we try to optimize the centroid, right? So uh, for the iteration, in the maximum iteration, what is defined here, we try to first calculate or create clusters. So create cluster, what is doing, I already explained. Create cluster is nothing but doing step 2 and step 3, that is finding the distance between each data point and assigning the data point to a particular cluster where the distance is minimum. So that is what this function is doing, these two functions, create a cluster and closest centroid. So once the assignment is done, then you try to find out the new centroids by using this function called get centroids, where it is calculating the mean of the clusters. So once the mean is determined, it will assign that mean as the new centroid. So once you have the old centroid and the new centroid, you basically have to see the convergence, right? So when do we say it's converged? We say it's converged when the distance between the old centroid and the new centroid is 0. So I have done, I've created a blob using a simple sklearn data sets, and I've tried to predict this. So here you can see initially I've given k value equal to 3. Okay, clusters equal to 3. So what I've done here is, in the first step It is trying to randomly initialize the cluster. Okay, in the next step, when it's trying to find the mean, you can see the data points getting adjusted according to uh, the mean value or the new centroids. This goes on until these are better clustered, as shown here. So you can see that now they are clearly distinguished. Each of the clusters are clearly distinguished based on these centroids, and you won't really find the difference in the mean value between the previous step and the next step, only a slight difference. And that's the reason why iterations have stopped. So see, the convergence can be, this operation can be stopped by two steps. Either it would reach the maximum number of iterations, or it should have reached the convergence. So either way, in either case, it will stop. Say, so let's say for in this case, if I given max iteration is 50, and if it is not able to converge within 50 iterations, still it will stop because the max iteration has reached, and it will give the best possible cluster at the end of 50th iteration. Hope this is clear. uh, I have a couple of questions asked by the audience. How do we prevent overfitting? I mean, there is no question of overfitting here, since uh, you don't have a label or y label here. What do you mean by overfitting? Could you just elaborate a little? What do you mean by overfitting in this case? See, in unsupervised
No,
learning,
the question would be the pipeline of machine learning model training. So let's say, do you have a training and predict phase separately? Or when I put
no.
this model in
See,
production,
yeah,
do I have
yeah.
to train the model all over again for new inference data?
See, that is the fundamental of unsupervised learning, is that there is no training as such, right? You are doing real-time clustering.
So it only
See,
has only one instance, one run. You don't do
yeah.
training and inference separately. Everything is
So
inference, everything is training and inference combined, right?
yeah, so that's why you don't see something called fit and predict. We are just using
Right.
one function called predict. Now the question. Okay, let me just rephrase that question a little. So once I determine a sort of clustering, I get these hyperparameters like k value and maximum iteration, etc. I fix that. Then I have a new data which is similar to the ones which has been already clustered. Then definitely you can use the same variables. But if the data itself is very different from the previously clustered data, then you cannot use those same
No,
parameters.
let me ask a scenario here. Let's say COVID-19 is going on. Hospitals are filled with patients, right? And these are
Mhm.
unsupervised learning situations. Hospital have to do segmentation or clustering of patients. High risk,
Mhm.
low risk, medium risk, right? Now the
Mhm.
problem is, one hospital runs an AI algorithm with clustering and says, okay, these are high, low, and medium risk patients. Three clusters are created. But in next
Mhm.
1 week or every day, they get a lot many new patients walking into the hospital with the COVID symptoms. Now they have
Yeah.
to run clustering again and again. Every day they have to run clustering on the entire data set, right?
Now that then you'll have
There
to
is no
ask the
concept of
question.
incremental learning here.
Yeah. No. Like then you'll have to. Then I would ask a question. How the parameters of the new patient and the old patients are related? Are they similar? Then you can use the same cluster configuration. If they are not similar,
So
then
I'm thinking
your
in that situation, you may have to do what we call a semi-supervised learning. So you have
yeah,
developed the average feature vector of the patient so far, and then you
yeah,
just compare any new patient walking in. And so basically you create labels by unsupervised learning. So unsupervised learning
yes,
leads to
exactly,
label creation, which is then
exactly,
used for inference on a new patient. Okay.
exactly. So that was one of the applications when we discussed in the first module, where can we use
Hmm.
unsupervised learning. So to create labels for supervised learning, we can make use of clustering.
Right. Precisely. Correct. Correct. So then you can do the usual inference mode once you're
Yeah.
able to do that. Yeah.
Okay. Uh, Let me take a couple more questions. Okay, there was one question. How do we ensure that next centroids are farthest from all the previous centroid instead of the first centroid? I hope you understood when I said how the new centroid has been calculated. So here, the new centroid is calculated not based on the first centroid alone. Okay, so let's say the second centroid is this. Now the third centroid is not dependent on this, but it's dependent on this, the previously selected centroids. I hope that answered your question. Fine. So see, there are lot of implementation of k-means with respect to deep learning, and maybe we may not have the time to go through these research papers, but I would encourage people to go through this research paper where they have used k-means for weight sharing and sort of like compressive convolutions. So I'll share these research papers, and you can see where all k-means are used. And another interesting application of k-means is for oversampling for imbalanced learning. So I would encourage participants to go through this paper. Very interesting. So they are just not used just for this kind of clustering. There are a lot of other applications where you can, as we were discussing, that you can use clustering for as a first stage before supervised learning. Like that, clustering can be used as like sort of a pre-processing method for further machine learning operation. Is that clear? Okay, let us, before moving further, I would like to give another 2-3 minutes for audience to ask questions. I mean, till now, if you have any questions, please ask me in the chat. I'll try to answer them. Okay, I do not see any questions.
A few questions in the questions list. So were you able to address
Yeah,
all the
yeah,
ones which came
yeah,
before?
yeah. We have answered all the questions. Okay, fine. Let's move ahead. Let's see the next topic, which is nothing but evaluation metrics. Okay. Uh, when I had to come up with the evaluation metrics for unsupervised learning, I was in a dilemma what all evaluation metrics I have to select for this session. Uh, because you have two types of evaluation metrics, if I can say, called as internal indices and external indices. Okay. Now, most of the unsupervised learning metrics are internal indices where the metrics are not dependent on any labels. Okay, where the evaluation metrics are not dependent on the labels, because definitely in unsupervised learning you don't have any labels. So in those scenario, we call those evaluation metrics as internal indices. And whenever we have the external or labels, any external data to compare with, then we call them as external indices. So in today's session, we have both the type of I have used both the type of evaluation metrics. The first two are nothing but your internal indices, where it's not dependent on the predicted, the label y, whereas the next two metrics are dependent on the label Why? Then you might ask a question, since in unsupervised learning you don't have a label y, how will we make use of these evaluation metrics? I mean, that's a good question and it's a valid question. I was thinking of a scenario where you have a group of data, but you have only labels for a certain set of data. In that case, when you want to, and you know both the data are similar to each other somehow, in that case you want to just stabilize your clustering model. In that case, you can use these external indices of completeness score and contingency matrix. But in most of the scenario in unsupervised learning, we'll have to rely on the external indices such as inertia and slot score, where you don't have y label. But let's say in some scenarios you do have y label for some data set out of a group of data or out of a large quantity of data set, then just for a check, how it is working, to get some confidence, you can use the other two evaluation metrics. So apart from inertia and slot score, you have various other internal indices evaluation metrics, which we'll discuss when we go to the next module, where we'll be discussing advanced clustering. We'll cover few more of internal indices where you don't need labels to evaluate your model. So today we'll be discussing four evaluation metrics. One is the inertia, second is the slot score, very very important. I would say if you had to pick one evaluation metrics from today's session, you will have to focus on slot score. Okay, then you have something called completeness score and the contingency matrix. So let us cover each one of them one by one and try to understand what these are. Okay, someone asked me a question, how do we decide k clusters, right? So you can decide the value of k based on inertia or based on minimizing the inertia. So what is this inertia? Inertia is nothing but the average intra-cluster distance between samples and its centroid. So if I have a centroid, okay, and the data points, inertia is nothing but distance between this centroid and these data points, the average distance. So when we try to plot this inertia value for different clusters, you will see that at some point the cluster will, the inertia will randomly reduce, will try to go down drastically. So this is also called as the elbow method, as it represents the elbow. So at this point, whichever corresponding cluster is shown, you can select that as the k value, and you can say, okay, beyond this point there is no point in increasing the k clusters, the value of k, because the inertia is not going any further and it's sort of like minimized. So when you say the minimization of inertia, if you think intuitively, you are seeing that there is no further change in this mean value. Okay, it's not going to change any further for the given centroid or for the given cluster, and convergence is achieved. So it's also sort of reassuring that we have reached the convergence for given number of iterations and the given number of k values. Okay, so in this case, let's say we can stop at say 5 or 6 and say this is sufficient for me, this k value is sufficient for me because the inertia has been minimized. Now, will this work at all times? Okay, let me give you a scenario. Okay, in this case, yeah, you got a point, right, to select. This is my k value, this is going to be my k value. But if you have a slope something like this, okay, then how do you decide which k value to go? Then it becomes very tricky, and you'll have to see other evaluation parameters to decide k value. So yeah, so you can use this as a first evaluation to check whether the cluster or the number of clusters is sufficient or not. but it might not work at all times. Yeah, so when you are increasing the number of clusters, you are creating more cohesive groups, and that's the reason why inertia is reducing. So you are creating more cohesiveness. So I already told you what is cohesiveness. So you're trying to increase the cohesiveness and maximize the separation, which is leading to reduction in the inertia. Is this clear? Is the inertia clear? I think it's a very simple metrics. If you
Yeah, so
have not,
just to augment that, so it represents, how tight the clusters are, because x minus mu k would be minimized if the
yes,
x for that cluster are very close to the centroid. So it's like three classes and three class monitors. So every class has only students which are very close to the class monitor. Right? So they are tight buddies. It's about measuring the tightness in clusters or tight buddies around the three class monitors for three clusters. So the question, another follow-up question could be, how do you even get started? Before you have this calculation going on with hit and trial with multiple clusters, how do you even
hmm,
get started? So that's where the domain expertise is the only solution. So
yeah,
in the healthcare scenario, when I'm starting day one, I would just assume that there are, let's say, three levels of critical patients, high risk patients, medium risk, low risk, and I will not have any other. Based on my the medical expertise of the hospital, they will just classify them into. They'll start with three as the number, and from there they will iterate, and this kind of formula will kick in. But before you have this formula kick in, you'll have to just apply domain expertise. There is no fixed way of determining k before the calculations are started. Just to augment that a little bit. That's all.
yeah. So audience, any questions on inertia? Okay, I don't see any questions. So I'm moving ahead. Yes, this is a very important metric called the Silhouette score. See, a Silhouette score is a measure of how similar an object is to its own cluster compared to other clusters. So it simply we are asking a question with the help of Silhouette score whether this data point is better suited in this cluster or is better suited in this cluster. So this value will help us will tell us whether all the data points belonging to a particular cluster, does it actually belong to that cluster or not. So it value ranges from -1 to +1, and negative value means that it is the cluster is very bad, and +1 means the cluster is very good. So -1 would indicate that few data points belonging to this cluster should actually belong to some other cluster and not this cluster. Okay, and a data point and a +1 would ensure that all the data points belonging for that particular cluster actually belongs to that cluster itself. So how is this calculated? So it is calculated as a difference between b minus a divided by, or you're just normalizing that uh, with help of the maximum of a and b. Okay, here a is called as cohesion and b is called as separation. Okay, by this time you would have known what is cohesion and separation. So when you're calculating a, what you're doing is you're taking, let's say you have two clusters. In a, you're taking a particular data point and calculating its distance with respect to its own group. So for each data point, it will calculate the distance to its own group, and you will have an average value. So that is your cohesion. And separation is nothing but you take a data point belonging to this cluster and you calculate it with respect to data points of the nearest cluster. Okay, how far or how close it is. So you do this for each and every data point belonging to this particular cluster. So that is your separation. So what you're then trying to do is subtracting the separation with cohesion and then trying to normalize with the larger value. You see, when will we get -1? Okay, when do we get -1? So I told you that -1 is bad cluster and +1 is good cluster. So we will get -1 when the separation is low compared to cohesion, right? So if I have a high separation value, intuitively it means that the clusters are far away from each other, and the data point belonging to this cluster is there is no chance that it can belong to this cluster because the B value is very large enough. But in the other scenario, if you have something like this, two clusters, there will be a chance when the cohesion will be higher compared to your separation. Then it means that there is a chance that that particular data point or data points belonging to one particular cluster is it should have belonged to some other cluster. I hope this is understood because it's a very intuitive way of understanding slot score. So if the separation value is high, it means the two clusters are far away and the data point belonging to one cluster cannot belong to the other cluster since the B value is large enough. Because B value is nothing but the distance between the data point of one cluster to the data points of other clusters. It's the average distance. And cohesion is nothing but distance of a data point between the data points of the same cluster, the average distance. So if you have higher B value, there is a good separation, and that's why you get a positive value of +1 because you are normalizing it, so the value will range from minus to +1. And since you are not taking any mod, that's why you get a negative sign. Okay, so you should always ensure that you don't have any negative slot score for any of the clusters. So here you check the slot score for each of the clusters. So for cluster one clusters, in this case I have used two clusters, but this may not be a very good clustering. Okay, so I go and I take a cluster or four clusters. In this you can see the slot coefficient value of cluster 0 has increased from say 0.6 to 0.8 plus. It is getting closer to 1 with more number of clusters. So that is one of so hence slot score is one of the very important metrics which is used in unsupervised learning. So if you notice, both these inertia and slot score is dependent on only two things: cohesion and separation. So the first point which we discussed in hard clustering, the property of cohesion and separation must be valid, right? Because it is based on these two properties that the other subsequent steps are taking place. So even when we are using these evaluation metrics, we are again going back to the fundamentals of hard clustering, that is cohesion, principle of cohesion, and maximum separation. So I hope the slot score is clear. If it's not
Yeah,
clear,
I'm
please
thinking
ask.
of another crude analogy. So the point
Mm-hmm,
is, a person is very close to their family members, and the
mm-hmm,
degree of closeness with family member is more than their degree of aversion with outsiders. So,
yeah,
uh, so, so, so the distance from outside. So, person is a recluse, but very recluse in terms of outsider, but very, very tightly knit with their family, right? So the distance from outsider is very large, whereas the distance to immediate family is very small. So that
exactly.
indicates a very tight clustering. Okay, yeah.
So yeah, so if you can understand separation and cohesion, then you can understand most of these evaluation metrics since they are dependent on them. So as I was telling, if the separation is very high, so you will ensure that the data point belonging to this one particular cluster has no chance of belonging to some other cluster. Okay, so moving ahead is something called completeness score. And I told you the completeness score and the next contingency matrix are are external indices evaluation metrics where you need label Y. Okay, so if you want to calculate the completeness score, then you will need to have the labels. So here the completeness score is given by C equal to 1 minus h of k comma c divided by h of k. This might be a little tricky to understand, so I would put this into some other formula. Say to simplify this, C equal to 1 minus h of y predicted plus y true divided by h of y predicted. Okay, what is h? H is your entropy. So your h, what does entropy mean? So entropy means disorderness. Okay, so if there is high disorder in your data, then the completeness scores go down. And if there is low disorderness in your data, the completeness score increases. So completeness score is telling us whether all data points belonging to the same class are clustered into the same, or same class are clustered into the same cluster. So if I have label of say a diabetic and non-diabetic, and if I build two clusters of diabetic and non-diabetic, I need to make sure that there is no diabetic patient going into non-diabetic and a non-diabetic patient coming into a diabetic cluster. That is what completeness score means in a very simplified manner. So you can calculate that using the entropy function. So it is given by 1 minus h of ypred slash y true and h of ypred. So this is known as conditional entropy. Okay, this is known as conditional entropy, like your conditional probability. It's called as conditional entropy, where you are calculating what is the entropy of y predicted given y true, you know, where you have a label. So y pred can be given as, let's say, something like this. You know, I don't want to go in depth of entropy, but if you want to ask what is entropy, I think you would have come across entropy in any of the classification errors. You know, if you are using any logits function or any of these functions, you would have come across the term cross entropy loss, right? So there, what are you checking? You are checking whether whatever has been classified is correct or not using the help of a log function, a log metric. So you are using the same thing here, except for a conditional entropy divided by the entropy of the y predicted. So this ratio, if this ratio is very high, then you will get C equal to 0, which means there is the clustering is absolutely wrong. Okay, and if you have an ideal scenario where there is no disorder in your disorder means wrong clustering, then you will get a perfect score of C equal to 1. Yes. So there is a question here. How do you know Y true, since for unsupervised learning, you don't have the Y true? That's a good question. So I'm telling you, you can use these evaluation metrics where say, yeah, one point is, yeah, if you have the domain expertise, or if you have the Y truth for a small data set out of a big data set, only for small data set, you have the Y true, and you can use that to check how good your clustering algorithm has performed. So in a given large data set of unlabeled data, if you have small data set with labeled with some sort of label, you can then make use of completeness score. But if that is not available, then definitely you cannot use completeness score. So that's why I told that I told of two different types of evaluation metrics, the external and the internal.
Is A the probability of C belonging to K cluster? ACK is A the probability?
ACK is nothing but number of samples with A is nothing but number of samples with K assigned label K. So this is label K assigned to cluster C. It is not a probability. So if I say okay, if I
Okay,
say
yeah, that's
A
fine.
of
I think
C,
the maths may be a bit more extended discussion, so yeah,
I
so
think
that's fine.
yeah, I will come back to this because I will have to explain this in a much more detailed manner to explain entropy. But if you have any
Yeah.
similarity with cross entropy loss, it becomes much simpler because
Hmm.
it is nothing but it's nothing but your cross entropy loss. But I will try to come back to this after we finish the you know the code demo of breast cancer analysis. Probably, if time permits, we'll come back and we'll discuss this a little more in depth. Okay, then you have something called as contingency matrix. So contingency matrix, by this matrix, you would have known that this is something similar to your, what you used in supervised learning, right? So you have the zero label. So how many predicted and true labels fall into this category, and how many are, so these are your proper clustered and these are your false clustered. So it's supposed to be clustered as 1, but it's clustered as 0, and this is supposed to be clustered as 0, but it's clustered as 1. So this is your equivalent of what you see in supervised learning. In unsupervised learning, you call this as contingency matrix. Any doubts on this before we go to code demo?
So it's like confusion matrix.
Yeah, the confusion matrix. It's an equivalent to confusion matrix. There it was with respect to classification. Here it's with respect to clustering. And you can have here n number of clusters. And all these diagonal values will tell you how good your clustering algorithm has performed. Okay, fine. So if there are no questions, let's move on to the code demo. Okay. Yeah, so you can get the breast cancer data from this link. I have already downloaded that data and I've placed it in the temporary storage here. So if you want to, if I provide this code link, notebook, and if you want to perform this analysis, please download from here. Okay, these are nothing but your libraries, required libraries. These are your column names. So in today's session, I have taken a data set which has labels. So since this is our first session on clustering, I thought we can have some sort of a comparison to see how good our, clustering algorithm has performed. So that's the reason why I've taken this data set. But maybe going forward, we'll not have any uh, Y labels at all. So these are the column names or the features which it has. First, it has the some sort of patient ID. Okay, so whether they are diagnosed as malignant or benign. So malignant means it is cancerous. Benign B means it's non-cancerous. Okay, then you have the the features of that tissue, like like whether what is the radius, mean radius, what is the texture, perimeter, etc. So this was one of the famous problem in Kaggle, which they had asked to solve using supervised learning, definitely not using unsupervised learning. So I have picked this data set so we can perform this clustering and see how well it has performed. So radius is nothing but the, for each cell nucleus, what is the mean distance from its center to points on the perimeter. So like that, you have like 10 features. You can go through this constant data to understand this better. Fine. So I've done some feature, EDA just to understand how the data looks. So if you see this pair plot, let me just zoom out a little. So blue is malignant and B is benign. You can see that at some point, the perimeter and the area mean, or a given perimeter mean and area mean, at some point it gets classified into benign and malignant. At this point, let's say for 100, from 100 to 1000. So at this value, it gets split into the benign and malignant. Similarly, here you see a horizontal separation. So here it's a linear separation here and here, but here you see a horizontal separation for different uh, combination of features. Similarly, here you see a vertical separation between smoothness and perimeter mean, how it's getting classified into benign and malignant. But we cannot see them as individual features or combination of couple of features, because at the end it is the combination of all the features that would classify it as benign or malignant. Okay, so what we'll try to do is, then I would try to adopt the diagnosis, because for going forward we'll not need the wipe red for our K-means algorithm. So, and one more important thing, what I want to tell you is I have imported the K-means from sklearn, okay, dot cluster K-means. So here K-means by default will use K-means plus plus for initialization. So always remember that if you're using K-means using sklearn, it by default uses the initialization of K-means plus plus. So you don't have to worry about the initialization factor. Okay, to see these are not in 2 dimensions, so there are n number of parameters, right? So I want to see this and reduce this dimension and make it 2 dimension, and for that I've used another library called tsne, okay, a manifold library. So we'll cover this when we discuss about dimensionality reduction in future sessions. So when I do this, we get something like this. So here you can see the malignant and benign, and as we were discussing the different different the big or the small, within malignant you can see different clusters. You see here small radiuses of the area mean, and here you see the area of the cancerous being very large for bottom half. Let's say at -20 and below, you have a clear classification of malignant. Yeah, and above this you have uh, the benign. But in between, let's say 0 and -20, you have, it's like sort of overlapping, and it is because this is a non-convex cluster. Okay, it is not a straightforward clustering, it's non-convex cluster. So I took this example also to show you this, that in these kind of cases, you even when right from the start, when you do these EDAs, which is mandatory to do, you will get some idea as to whether I have to use k-means or not, because from this you can see that they are overlapping, and you cannot expect k-means to cluster them into cluster them very well, because they are overlapping and it is not non-convex problem. But still, for this study we'll use k-means because we are not we have not gone through the other clustering algorithms. So I'll cluster into 2 types, because let's say I am a doctor, I know that the cluster it has to be separated into either malignant or benign. So I'll use K as 2, cluster as 2, and I'll do max iteration as 1000, and I'll use a random state just to get reproducibility. I'll use this predict function on this data, okay, with diagnosis feature dropped, and let me plot this. So here you can see the malignant and the benign. So as I was telling before, here we could clearly see that there is overlap of benign and malignant. But when we feed it to our clustering algorithm of K-means, it, it is impossible for K-means to classify and filter out the malignant out of the benign. You can see it has clearly made a demarcation or a boundary for below -20 uh, as malignant and above -20 as benign. So it is not able to pick up these points, okay, correctly classify these points. And you don't also expect K-means to do that, because K-means, as I told, does not work very well with non-convex problems. So this is one of the best examples. That's why I took this data just to show you like what can go wrong. And if you are not, let's imagine that you didn't have this uh, white truth, or yeah, white truth, then definitely whatever you got here is wrong. It's not absolutely correct. Yeah, it's approximately correct, but it is not clustered perfectly. Okay, so we will check this with inertia. So I've seen whether the number of clusters of 2 is sufficient or not. So when I plot this, I can see that for 2 the inertia is very high. Okay, definitely it's not small inertia, it's very large inertia. So is 2 good enough? No, it's not good enough, because there are other things what you can derive out of this data. So as we were discussing a while back, can we classify them as, you know uh, severe, non-severe, or medium severe? So that kind of information with 2 cluster is lost, and that is what this inertia is telling us. See, if you see this data, you can see, right, the smaller ones and the larger ones. So clearly there's a different, within malignant there's a different classification happening. So that this is not able to capture, and that is what is shown in inertia value. So ideally we would have to select somewhere between 8 clusters. Yeah, 6 to 8 clusters would be ideal. Okay, then Silhouette score. Okay, I've selected for 2 clusters as well as 4 clusters what would be the slot score, and I've plotted that. So here you can see that there are some negative values. Okay, and you, as I was telling, negative values do not indicate, or they indicate that the clustering is not good enough. So with 2 clusters you have a negative value. Even with 4 clusters you still have negative value. But so that so so what you can, now you have understood that from the inertia the ideal would be 8. So I would encourage all of you to try this out with 8 clusters and see how the silhouette score looks like. So when you will try with 8 clusters, you will see that this negative value decreases and this positive value for each of this cluster increases to capture the information much better. Okay, then you have the contingency matrix. So you have the positive values here. So 83 of them have been classified, points have been classified wrongly compared to, you know uh, out of the whole data set. So this is possible because we have uh, the prediction, the diagnosis labels. If this was not available, we could have not found out the contingency matrix and the completeness score. So completeness score is far away from 1, right? So it is definitely not a good value with 2 clusters. So we will have to use more number of uh, clusters to have a better inertia, better silhouette score, better contingency matrix, and better completeness. So when you try this with new or higher clusters, you will see it better, better clustering. Definitely I don't expect k-means to cluster this, as benign and malignant, but definitely you can see better clustering with these points, these data points, or these data points here. So you will find this as one separate cluster, this as another separate cluster, etc. Hope you have understood. So maybe when I share this notebook, you can try for different values of clusters and see how they behave and how these plots are changing. So you will get better insight, because in unsupervised learning, it's all trial and error. So as you try with different iterations and different values, you get new insights. Okay, and at some point, it becomes clearer and clearer. But from one point, what I want to again reaffirm is that if you have a data set, something like this, please do not expect K-means to perform it very well clustering, because it violates the convex rule, which is mandatory for K-means clustering. Fine. If you have any questions, please shoot your questions.
Okay, that was great. Audience, any questions?
Okay, if not, going to the summary. So we have covered what is clustering. Okay, we saw the different types of clustering, the hard clustering and soft clustering, and what is the properties of hard clustering, the maximum cohesion and maximum separation, the convex and non-convex clusters. Then we saw various distance functions. Out of that, we made use of Euclidean distance for K-means algorithm. And we saw how we can improve the initialization with K-means plus plus algorithm. And we also saw the various evaluation metrics with which you can you know confirm whether the clustering, whatever we have done, is good enough or not. So out of that, inertia and Szilard score are your uh, internal indices, evaluation metrics, and completeness score and contingency matrix are your external indices, where you need a white true to calculate these evaluation metrics. Yeah, so that's it for today's session. In the next session, we will be covering uh, the advanced clustering. So today we just covered K-means and K-means plus plus, which was the basic form of clustering. But going forward, we'll cover some of the advanced clustering methods, wherein we can see how we can avoid the disadvantages of K-means, which you just saw, with the better techniques, and we will also see better evaluation metrics, which are more of internal indices and less of external indices, because going ahead, we will assume that we do not have y true, and with that condition, how do we evaluate our clustering? So that would be a challenge, and it will also be very interesting to see that scenario. Okay, that's it from my end. So if you have any questions, please ask me.
Yeah, you can see, I think one or two questions are there.
How do we transform textual data into these points in the n-dimensional space? Textual data may be converted into vectors, and then we can probably see how it will be done. I think this is more with regards to NLP, if I'm not wrong. Vivek, you have any points on that because it's related to NLP. So the question is, how do we transform textual data into these points in n-dimensional space?
No, that we do using normal NLTK techniques, right? You
So you are
vectorize.
basically yeah, it's basically vector itself, right? Not nothing more to
Yeah,
that.
you do embedding. You convert word to vector, word to vec.
Oh, okay. Yeah. So that was the answer. So you will have to convert them into vectors and then do clustering.
Any other questions, folks? So there are some good comments coming. Code can be shared with the AI lab members. So there is a question if code will be shared, it can be provided to lab members. And very comprehensive, nice session. So thanks for that to Nikhil. Any other final comments or questions, audience? It was a very detailed session, very well presented and fabulous content as well. Very intricate explanations.
Yeah. So if you have any suggestions on how we can improve the next session, please put that as well so we can do better in the next session. So when we are going ahead, we'll be covering a few advanced topics. So if you have any suggestions for us, then it will be very good that we will definitely try to incorporate those suggestions in our future webinars.
Nikhil, this breast cancer problem, this is
Mm,
pretty decent problem for our product team, no? So shouldn't we be deploying this in the product team?
I mean, those, yeah, if you have those metrics, you can do it as a first-hand insight. I would say, see, we cannot use that as classifying as malignant or benign because that would be a very crude way of doing it. But if you want to get just the insight of those data points, we can use as a pre-processing step. But it may not be very good to use unsupervised learning for medical,
No,
just
in
to.
your data set, you said you have the label. So the problem looks very important and good one to solve if we can. So if you have the label in the data set, we should deploy this as a product.
Yeah, I mean that should be done definitely. Yeah, I mean you are referring to supervised learning, isn't it? In a
Yes,
supervised
yes.
learning. Yeah, yeah, definitely. Yeah.
Okay, so in interest of time, so that's it for today, folks. So thanks a lot to Nikhil Narayan. Excellent session. Very meticulously presented as usual. And Nikhil continues to raise the bar for us. And thank you, Nikhil. And thank you, audience, for lots of questions you have asked and engaging with us. And we see you in our next webinar. So see you all. Have a good night or good day as the case may be.
Yeah. Thank you all.